So yesterday, you spent time looking at the different tools that are available for preparing data, for making maps, and for making maps using QGIS. And you also were looking at, for an example, one of the examples you looked at yesterday was the crater Tchaikovsky on the lunar far side. And today, I want to take a slightly different perspective and talk to you about the processes that happen during impact cratering and what the morphologies look like, because it's important to understand the geological processes. Let's see if I can advance my slide. There we go. It's important to understand the geologic processes that you want to somehow identify in your map. So mapping is just one of a tool that you're going to use to develop a geologic framework to understand the geologic history of the surface that you're looking at, either that local surface, or you can expand this up also to looking at the entire planet. And then at the end, go really big picture and compare the geological histories across different planetary bodies. And so we're just working on this week the surface mapping aspect of this development of a geologic framework. And what's really powerful about that is after you've done the mapping is that you can, for the moon, correlate the mapped units and what you've interpreted there from the remote sensing data. You can calibrate this with the collected samples from the moon. And this is really powerful and can be then extended to other planets. I'll talk a little bit about that later on in more detail. And so this all folds into understanding the geologic processes that are operating on the planet. And this is important for making maps, and making maps also helps you understand what processes might be happening on the planet. This is combined naturally with the work of the Europlanet RI project in terms of getting people into the field and looking at analog sites on the Earth, because it's important to use the Earth as an example for how these geologic processes work, how do we understand them, and how might they look in remote sensing data. So that's the perspective that I'm going to give you a presentation today about how impact craters form, what are the different types, and then how we can feed this into doing some more advanced techniques. So to start at the very basic, there are different impact crater types that you've probably noticed as you've been looking at different planetary surfaces. They range from simple craters, like the Fraumaro A crater here, that is just a simple bowl shape with a simple rim. And then they get more complex as they get larger. Here, the example of Tycho crater that has a central peak and a terraced crater wall. And then as the craters get bigger, they get even more complicated, more complex. Here, the example, the Schrödinger Basin with the a peak ring that has started to form. So there's not just a central peak, there's a ring that forms in the center. And then when we go to even larger craters, you're gonna have multi-ring basins. And the young, very clean, nice example from the moon is the Oriental Basin. And so there's a progression in size that's controlled then by the gravitational factor on the planetary body. I'll show you a plot of that in just a few minutes. So, and then the other thing we're going to look at in a little bit more detail are the formation stages that craters look that during crater formation, and what processes those involve and how they affect what the morphology is at the end. So just to quickly look at it in a general way, when a projectile impacts the surface, we end up with a shock wave that gets released because this is a hypervelocity event. Okay, that shock wave And that contact begins this first stage, which is the contacts and compression stage. So contact happens, then this pressure wave starts to move through the target here. And it's actually, this shock wave is actually causing material to start to flow away from the point of contact. Okay, then there's a reflection of this shock wave called a refraction or release wave. And this is the point at which you start to move into the next stage called the excavation stage, because this refraction wave starts to then push material back out of this hole that has been forming. Okay, so then we move into the excavation stage and we get the ejecta curtain forming. There's vapor, there's melted material because of the pressures that are achieved are up to about 100 gigapascals, and that's a high enough pressure to vaporize and melt material. Okay, so that stuff starts to then be ejected. When we move farther along in the excavation stage, the material has then stopped kind of moving through outward from what's called the transient cavity, because all of the energy that has just been deposited into that target has been used up. And then basically we move into what's called the modification stage. And so this is a kind of where everything starts to settle out and the rocks compensate, and you end up with moving towards what the final crater is going to look like. So the modification stage has the deposition of the ejecta finally. Okay, then material starts to move in to fill this transient cavity that's not a stable, gravitationally stable shape. Material starts to move down into the crater to fill in and basically isostatically then compensate everything. And so at the end, the final crater is not as deep as a transient cavity, and it's filled with melt-rich material and breccias. There's at the end the ejecta blanket that extends away from the rim. The rim is uplifted slightly. And then, of course, there's a lot of fractured rock underneath in the basement, underneath the crater, due to the propagation of the shock wave through them. So those are the crater formation stages. And the information that we have about this and how this process works has been taken from studies of terrestrial impact craters and laboratory investigations. And so that's why we can look at this sort of in a 3D view and a cross-section view to understand the process. And so then we can apply it to looking at remote sensing data and understanding maybe what kinds of rock material and different morphologies are visible. Okay, so I want to step through now and look a little bit more in detail at the simple craters and the complex craters, so that you can start getting a feeling for what they look like in cross-section versus in map view when you would be making a geologic map out of it. And so this is a nice example of a simple crater on the moon that's about 2.5 kilometers across. And on the moon, simple craters are less than about 20 kilometers in diameter. This is just a particularly small one, as in that nice fresh example. They're bowl-shaped, like I mentioned. There's not any major slumping on the walls, so they don't have these what are called terraces. We'll see terraces in the complex craters. And there's not a central peak. Okay, so that you can also see in the map view. You can also see this in the cross-section, that there's a simple crater rim. There's not a lot of slumping. I mean, there's no kind of, listric fault things going on there. There's just debris that kind of slides down the slopes into the center part of the crater. And there's not a central peak. You can see that even below the crater, there's just fractured material, and there hasn't been sort of an welling here up, sort of bringing up from depth of material due to the impact process. And then you can't see it in this picture, but we'll see in another picture that there is ejecta that is about 2 to 3 crater radii beyond the rim. When it's fresh, you'll be able to see this. If it's an older crater, that gets degraded, and it's going to be harder over time to see it. Also, the depth to diameter range is pretty well studied, and so the depth is about 1 to depth to diameter ratio is about 1 to 5 to 1 to 6 for the simple craters. Although that's something that also people look at in great detail, because it partly depends on what kinds of rocks are being impacted, and so that's just some interesting details that still are being worked out. And then typically for the simple craters, the rim height is about 4% of the diameter, so that it stands up above the original surface elevation. And so the impact velocity for these is well, I mean, it's a hypervelocity crater. There's still shock and pressure, high pressures involved in here. So it's greater than a few kilometers per second is the impact velocity for these types of craters. So here you can see both in the map view and sort of a cross section how the simple crater works out. In this map view, you can also see here in the center a small amount of impact melt that collected in the bottom. One of the most classic examples of a simple crater is the Beringer crater or meteor crater in Arizona in the US. And just to show you an example of one on the Earth compared with this lunar example that we had, it was formed by a large, a heavy 100,000 tons iron meteorite or iron. It's a sort of a mini asteroid, right? Which was 30 meters in diameter and had presumably about 20 kilometers per second impact velocity. So taking a little bit more detailed look at the formation of the simple crater, just to again repeat the process of the formation of the crater so that you can see it here displayed in a different way. For the simple crater, we basically just have the projectile is impacting the surface, forming the shock wave in the contact and compression stage as this wave moves out into the target. Material starts flowing outwards from the crater down and out as the shock wave continues through the material. And the refraction wave, it's kind of a reflection, starts to go in the opposite direction and starts causing the ejection of the material. Okay. For and then of course you've got vapor and melt involved here, even though it's a small crater. There's not a lot of that, but it still happens. And what you can see for the transient gravity for a simple crater, here's where the difference starts. Transient cavity is relatively small because it's a small impact. And so the basement underneath gets kind of pushed down, and this is going to be all the fractured zone at the end. But we don't get a rebound of the basement underneath the central part of the crater. That's going to be different for the complex crater. Okay, and then this is essentially what we've seen now a couple times already, that then the material during the modification stage just falls down and goes into the center part of the crater just at, in small rock falls and things, and then there's some melt that's left over that may accumulate in the bottom of the crater, just like the example that I showed. Okay, so that's the simple crater and sort of the simple process of forming a crater as we've understood it from studying terrestrial craters and from laboratory experiments and models. What happens between having a simple crater and a complex crater? I mean, why is the difference? Why do we get a central peak? Well, we're going to look at the process in a moment, but what we do know from empirical observations is that the transition from the simple to complex crater morphology, it depends on size for a particular planet. You won't see a 2-kilometer crater on the moon that has a central peak. That doesn't happen. And that's because it depends on the formation of the central peak, and then ring systems depends on the size of the crater, and for the different planets, it depends on the gravitational pull of that planet, so the gravitational constant. So what we can see here's the crater diameter at which the transition from a simple to a complex crater happens, and the gravitational constant for the body. Okay, and what you can see is that on the moon, the gravity of course, the lowest of the different planets that we're comparing here, and the diameter at which the change to a complex crater happens is at about 20 kilometers. Okay, and the transition to a complex crater on the Earth happens at a much smaller diameter, so about 3 kilometers. Okay, so what does a complex crater look like in detail on the moon? Here is an example that's 114 kilometers in diameter. That's Moretus crater. It's on the southern lunar near side. And here is this central peak that defines it as being as one of the features of being a complex crater. And then there's also a broader terrace. What you can see here is that the wall of this crater is not just a simple smooth slope. It's got terraces, so parts of it that kind of then as a chunk move down into the center of the crater during the modification stage. Okay, and then there's a larger amount of fill here. In some craters, like the Copernicus and Tycho craters, which are younger, it's clear to see that material that's in the crater is impact melt, breccia, and impact melt deposits. For some older craters, you have to double check and make sure that the crater didn't get filled with Mare basalts or light plains deposits afterwards. Tsiolkovsky, which you looked at yesterday, is a complex crater that got filled by Mare basalts after its formation. So, but in this case, this also looks like impact melt sheet and impact debris that has filled Moretus crater. Okay, so what does this look like in cross section? It's more complicated than the simple crater. We've still got the ejecta on the outside with a rim that's uplifted, but here are these downshifted blocks, the terraces that have formed during the modification stage. We'll look at those diagrams again in a moment. Then you've got breccias and impact melts that cover the floor. And then there's a uplifted section in the middle that's a central peak. Okay, and so these craters, these complex craters, like I mentioned, are on the moon about greater than about 15 to 20 kilometers in size, and on the Earth greater than 3 kilometers in size. Okay, yeah, and this depth to diameter ratio that we talked about before is shallower, okay, because this is much more flat, and that has to do with the fact, of course, that it is also related to gravity, because the crater is larger and there's more compensation that happens after the crater forms to fill in that hole, that the transient cavity. So let's look at that in terms of the same kinds of steps, but just a simplified view that we looked at for the simple crater. The contact and compression stage is essentially the same. So that's been left out here. Then we move into the excavation stage. Okay, that's also similar to the simple crater formation because you still have or I guess this is kind of the end of the compression and moving into the excavation stage where the shock wave has stopped marching outwards and material flow is going to stop and then start to kind of go back the other way. And that's what happens here, is that for a complex crater, the excavation of the transient cavity happens much deeper into the target rock. And then there's more compensation for that as that transient cavity starts to collapse and compensate gravitationally so that you get an upward motion of material in the center of the crater that ultimately forms the central peak, or also a central ring in the case of a crater that's even bigger. Okay, so here we still have deposition of melts and ejecta, and then the compensation during the modification stage, the formation of these downdropped collapsed blocks to form the terraces. And then here we are with the final crater again with these different materials on the flat floor with the central uplift. So one thing you might notice is that many people are interested in perhaps exploring central peaks of craters or central ring peaks because they might actually give you access to material rocks that are normally not accessible from the surface. Okay, they've been uplifted. So that's sort of an interesting thing to keep in mind as we talk about landing site selection and traverse for tomorrow. Okay, so let's just have a quick look again here, just to review. We have the map view of the complex crater and the cross section of the complex crater so that you all have in your mind as you're mapping craters, what that 3D geology is going to be looking like and what kinds of materials you're going to expect to see and might want to mark on your map. Okay, I'm not going to go into as much detail about the basins, but here's just an example. Basins on the moon form at about sizes greater than about 200 kilometers. And here in this case for Oriental, you can see that there are multiple large rings that form. And then in this case, these dark deposits here are Mare basalts that have filled in some of those troughs and a Mare deposit that filled in the center. Okay, but there is a lot of impact melt and impact materials associated with these terraces that have formed and the rings, and then also material that has been ejected out across a large part of the moon. You can find secondary craters from Oriental Basin. Okay, so just a quick mental preview for those materials that might be things that you want to map. And I'm sure that you saw some of them yesterday during the exercises to learn the tools, is that we've got here, this is Timocharis crater in Mare Imbrium. And what you can see is that it's a central peak crater, a complex crater, although there's a crater that formed right on the central peak, which is kind of funny. And you can see the terraces that have formed, the impact melt deposit in the center. There's the ejecta blanket, which you couldn't see in the other pictures that I'd shown you, but you can see here. This is why I've got this one out. And then you can see that there is sort of a texture that extends away. There's some discontinuous ejecta that you could map farther away. And then there are things like secondary crater chains here too, that are farther away from the crater. Okay. Now you're going to hear about more of these things tomorrow during the moon exercise, but I wanted to go ahead and just give this to you so that your eyes can start getting used to finding these things in the data. Okay, so craters. We've talked about how they form so that you have an idea about their geology and how this would help for your maps. But I also just want to briefly give you a little information about another way that you can use craters when you're making a map. And that is that you can use craters basically to help you build stratigraphic systems. So here I'm just going to give you the example really quick of the lunar stratigraphic system. Basically, it's based on the idea that you can use, that impact cratering is a process that happens over time, and that older surfaces have more craters on them than younger surfaces. And so what you can do without even measuring a number of craters and sizes of craters is you can assemble a stratigraphic system using the empirical observation of surfaces with more or fewer craters. And in this case, for the lunar stratigraphic system, there was some major basins that were selected then to serve as marker horizons, because of course we can't use things like fossils on the moon. And so the Nectaris basin is basically marking the progression from the pre-Nectarian to the Nectarian, and the Imbrian basin, the transition to the Imbrian time. Eratosthenian is defined by their Eratosthenes crater. And then the Copernican system, you can see there is a bit of disagreement about how long to actually mark it, partly because the Copernican system isn't defined specifically by Copernicus, but rather whether you can see the rays and ejecta from a crater or not. So you can make observations of crater frequency to give you an idea and to start sorting your geologic units into timescales and progressions of units. Because of course we want to get to a point where we can say in what order different things happened so that we can understand the geological history. So I just want to give you, I'm not going to go into details here because I'm already almost out of time, but what I want to point out is that there's a talk that I presented that's available as a link on the GMAP website, and we can put it with the course materials, where for those of you who want more details about using crater size frequency and actually applying it by measuring the craters, you can have a look at that talk because I go into 45 minutes of details. So that's an advertisement for that. And then we're going to skip forward to the application of it to having a look at the super big picture. Okay. So when you measure and count the craters on a geologic unit that you're interested in knowing how old it is, and you derive what's called an absolute model age, which is used, which is a lot. You can actually do it because this process is calibrated to the Apollo and Luna and now the Chang'e sample ages. You can actually now figure out ages for your geologic units across the entire moon, and come up with an idea of how, when, and how much, and you can really just then get a big picture of, in this case, the evolution of Mare basalt volcanism through time on the moon. Okay, and so then you have a tool which you can say, okay, I mean, here's the Procellarum terrain where there were a lot more radioactive elements for longer, and look, that is where the youngest volcanism has happened. Okay, and then these other basins, Tranquillitatis, Serenitatis, where these dark purple colors are, those are very old Mare basalts. And so we can start then to assemble a historical description of how the Mare basalts evolved over time. This isn't just possible with Mare basalts, but you can do light plains units or scarps and faults that form on the moon where you can get the data to measure their ages. So it's a really powerful tool. And it's not only useful for the moon, the lunar chronology has been adapted for use on Mars and on asteroids. Okay, so that's something then, bigger picture, we can start then to use that process to look at the setting up this lunar stratigraphy with actually sticking in, okay, when did Mare volcanism happen and in what parts of the moon? Here's the older Mare basalt emplacement, younger Mare basalt emplacement, and then also fit in whatever your favorite thing is for the moon, whether it be basin formation ages or light plains formation ages. And then we have an absolute time scale that we can use to compare with the Earth's history. And then we can actually start seeing, well, how does the lunar geologic history compare with the terrestrial history and the emergence of life, for example? There's a lot of stuff that happened on the moon and on the Earth even before life formed. And then we can take that to the level of the solar system, or all the terrestrial planets, and compare all of the planets and their periods of activity. And you can see that some planets don't have very much detail. For example, Venus, because most of the surface seems to be about 300 million years old, which is totally interesting on its own. And then Mercury is a bit enigmatic in terms of not really knowing exactly how the crater mechanics are affected by it being so hot there. It's so close to the sun where the impact velocities are higher. But we can at least start getting a feeling for the progression of events here. And then, of course, there's a lot of detailed work that has been done on the stratigraphy of Mars, and using craters for that has been particularly helpful in terms of dividing some of these smaller epochs into important stages of Martian history. And so all of this background information, I hope, will help you kind of see the bigger picture of where your maps are really critical elements of understanding planetary geology and comparative planetology. And then also just an important background that it's important to understand the geological processes that you're trying to map. Your maps will end up making more logical sense and be useful for more applications. If you always have in the back of your head what geologic processes it is that you're trying to represent in your map.